This video tutorial is for network analysis. Molecular networking groups metabolites that are structurally related, or have similar biological functions. It is widely used to identify unknown metabolites and discover novel metabolic pathways in metabolomics studies. For GCMS and LCMS-based metabolomics studies, molecular networking employs an algorithm to compare the similarities of fragmentation spectra, MS2, in each dataset, and generate a cosine score for each pair of MS2 spectra. When a pairwise spectral similarity alignment is performed, each MS2 spectrum in a given dataset is compared against every other, and a network of MS2 spectral relations is obtained, from which molecular networks are created. From a metabolomics perspective, one can regard mass spectrometry imaging as performing an MS1 level shotgun metabolic profiling at each pixel. Thus, due to the lack of MS2 in most mass spectrometry imaging studies, MS2 similarity-based molecular networking cannot be applied for mass spectrometry imaging dataset. However, it is also possible to group molecules with correlative spatial distribution into clusters. This is based on the assumption that functionally related molecules are spatially correlated. You can perform network analysis for all mass features collectively, or for each individual mass feature using ShinyCardinal. In this video tutorial, I will show you both options. If you are starting directly from this section, you will need to upload the RDS file in the Upload MSI Data module. Otherwise, you can proceed directly to perform network analysis. First, let me demonstrate how to perform network analysis for all mass features. If you have multiple MSI runs, please select one specific MSI run to perform network analysis. If you have only one MSI run, it will be automatically selected for you. It is important to note that network analysis for all mass features can be time-consuming, particularly for high mass resolution and high spatial resolution large MSI data set. In order to speed up network analysis, you have to option to subset the MSI data by selecting every nth pixel. For instance, by selecting every second pixel, that is 1, 3, 5, 7, etc., you can achieve a twofold increase in processing speed. Similarly, selecting every 10th pixel will result in a tenfold increase in speed. However, setting a larger value for n may result in underestimating or overestimating the spatial similarities between different mass features. Therefore, it is recommended to select the value for n thoughtfully. Initially, you can set a larger n to generate the network. If you discover something interesting, you can then adjust the value of n to a smaller one, or perform network analysis specifically for the desired mass features. You can click the Go button to start network analysis for all mass features. Once the network is generated, you can use the Navigate button to examine the results. This feature allows you to zoom in, move around, or reset the network to its original position. Additionally, you can click and drag a specific cluster to highlight it, providing a focused view of that particular cluster. Closely clustered mass features indicate that they have a similar spatial distribution. You can adjust the label size using the Set Label Size parameter. Furthermore, you can modify the spatial similarity threshold, which allows you to replot the network. Lowering the threshold value will lead to more mass features clustering together, while increasing the threshold will enhance specificity by reducing the number of clustered features. Our previous study showed that a threshold value of 0.9 or above can well group mass features that are derived from the same metabolite. You can click the Download button to download the network in HTML format. The workflow for network analysis for single mass feature is the same as that for all mass features, except that you need to enter the MZ value of the specific mass feature for network analysis. It is important to note that these two modules are independent from each other. You are not required to perform network analysis for all mass features before conducting network analysis for a specific mass feature. Feel free to analyze specific mass features without the need to perform a comprehensive analysis for all of them. In this demonstration, I will enter the mass feature 798.542 to examine which features are clustered with it. Simply click the Go button to initiate the analysis. You can see that 3 mass features are closely clustered with feature MZ798.542. As previously mentioned that, mass features exhibiting a spatial similarity of 0.9 and above have a high likelihood of being derived from the same metabolite. These highly clustered mass features are either isotope peaks, adducts, multimers or in-source fragments. Therefore, by examining the clustered mass features, we can potentially identify the metabolite associated with them. We can better examine their relationships using the generated pseudo-MS-MS spectra. You can clearly see that MZ799.545 is the C13 isotope of MZ798.542, and MZ740.472 is the C13 isotope of MZ739.469. The difference between MZ798.542 and MZ739.469 is 59 Dalton, which corresponds to the phosphatidylcholine head, trimethylamine. So the associated metabolite could be a phosphatidylcholine class lipid. We can search this mass feature MZ798.542 in Metabolite Identification module. And you can see, 2 types of candidates are given. One type of candidate is phosphatidylnolamine class lipid, and another type is phosphatidylcholine class lipid. We cannot identify this mass feature only based on the elemental composition because both candidates fall in the 5 ppm mass accuracy window. However, with the help of network analysis, this mass feature can be identified confidently as phosphatidylcholine class lipid, because a typical neutral loss of 59 Dalton is detected. By contrast, a neutral loss of 141 Dalton will be expected for a phosphatidylethanolamine class lipid. For more information on metabolite identification, please watch the metabolite identification video tutorial. To confirm these mass features indeed have similar spatial distribution, you can click the plot button to produce the ion images for each cluster feature. Please note that a maximum of 6 ion images will be displayed, but you can download ion images for all cluster features by clicking the download button. Similarly, you can increase or decrease the similarity threshold, which will result in either an increase or decrease in the number of clustered mass features.